Okay, so let's see. We've done domain, intercepts, symmetry, asymptotes, intervals of increase or decrease using the first derivative. We did the intervals. We determined local maximums or minimums. Now we have to do intervals of concavity. So our last step, intervals of concavity. And the intervals of concavity come from our second derivative. So our first derivative, or our first function, remember, was this. Remember, off camera, I determined that the first derivative was equal to this. And off camera, I went ahead and found the second derivative, which is equal, once simplified, to this. And again, that was done off camera, but it is a skill that you're expected to have. Make sure that you can do it. Camera, that's red. Where's blue? Camera. So make sure that you can do it. This is a skill you must be able to do. Okay, so what we need to do is we need to find all the critical values. We need to find all the places where the curve can change from increasing to decreasing. So, second derivative, critical values occur when f double prime of x equals 0 and when f double prime of x is undefined. It's the exact same as the first derivative. So the only difference is we've got a different function here. 0 equals 2 x minus 2 over x plus 1 to the 4. I like to pretend that there's a little 1 on the bottom there, and I cross multiply and I end up with 2. X minus 2 equals 0. Solving that for x, x must equal 2. So there's my first critical point. That means that it can change from concave up to concave down at x equals 2. This one, we're going to be undefined when x plus 1 to the 4 equals 0. Take the fourth root of both sides. Luckily for us that the fourth root of 0 is 0. Hey, I remember that. That's part of the vertical asymptote from the beginning. So that makes sense. So therefore, f of x can, not that it will, can change concavity at x equals -1 and x equals 2. So now what we do is we're going to take a look at an interval chart. Before I do that, let's make sure that we understand what's happening. If this is my Cartesian plane, what we're saying is at x equals -1 and at x equals 2, my concavity could change. Whatever the concavity is over here must stay the same up until this point. Then it has an opportunity to change. Whatever it is anywhere in this interval, it has to stay the same for that entire interval. And then it has an opportunity to change. And whatever it is right after 2, it has to stay the same for the rest of that domain. So the interval chart is going to be looking at everything up to, but not including -1. So x less than -1. The other part of the interval will be everything up to, but not including 2. Don't get hung up with this 0. It's just I'm trying to show you that it's not including -1. So -1 to 2. And then we're going to be interested in everything greater than 2. These will be my intervals on my interval chart. So, moving that off to the side, setting up my interval chart. And the interval chart is to determine the signs of f prime of x. Why do we want to do that? Because that will tell us about the concavity of f of x. So the chart is in fact going to be set up. Now the intervals are the easiest thing to put in first because we've talked about that. Oh, not 1, it's 2. Okay, those are your intervals. I'm interested in the sign of the second derivative, and that's going to be made up of a 2. Now, your teachers may have done this a little bit differently. I like to put the whole number there because it's going to be positive. We know 2 is always positive. If it was negative 2, then I'd put negative 2 and do negatives all down. The next one here is going to be the x minus 2. And the next one's going to be x plus 1 to the 4. And all of those are going to go together to give me a sign of the second derivative. That's what I'm interested in. And that sign of the second derivative, if it's positive, will indicate that f of x is in fact concave up during that interval. And if it's negative, it'll indicate that f of x is concave down. So this is the second derivative. I'm interested in its sign, and it tells me something about f of x. Now again, remember, it's not on the page here, but this was 2, x minus 2 over top of x plus 1 to the 4. So that is my second derivative, and you'll see where these values have come from. And I'm only interested in the sign. This is an even power, so no matter what this is, it's going to be positive. This will change. So if I put in an x value that's less than negative 1, like negative 3, that will be negative. If I put in 0, it'll be 0 minus 2, so that's negative. If I put in 5, that'll be positive. These constitute the sign that I get for the second derivative. Positive, negative, positive is going to be a negative. Positive, negative, positive is going to be a negative. Positive, positive, positive will give me a positive. That means that the second derivative is negative, less than 0 on this interval. So therefore, f of x is concave down on negative infinity to negative 1. This is going to indicate that f of x is concave down on negative 1 to 2. And this is going to indicate that f of x is concave up on 2 to infinity, forever. So that interval that we had, remember, where we went to negative 1 and we went up here to 2, you know that f double prime of x is less than 0 here, which means it's going to be concave down everywhere up to, but not including this one point. Remember, that's going to be your vertical asymptote. And f double prime of x is less than 0 in here, which means it's also going to be concave down. So it had a chance to change, but it's not going to. And from here, f double prime of x is in fact greater than 0. So it's going to be concave up from here on. That's what we know. All right, we're going to stop here, and then we'll put it all together.